Section 4.5 from our textbook dealing with exponential and logarithmic equations. We're going to start with trying to solve a series of exponential equations where our variable that we're trying to solve for lives in an exponent. And what we're going to find in this type of technique when we have a problem along these lines, one of the simplest ways is to take advantage of the following property. Very simple. If m is equal to n, then taking the log or the ln of m and taking the ln of n, you're going to get the exact same answer. M equals n, log base 10, log base 2 of m equals log base 2, log base 10, whatever it happens to be, that same base, we can say and attain equivalencies. And the reason we're going to do this in a lot of the problems is because where do we notice our variable is? It's an exponent. And with logarithms, what do we know? When you're taking the logarithm of something that has an exponent in it, the power property is going to allow us to drag that power, that exponent, to the front. And that's going to set us free to solve a number of these problems. In class, we had done numbers 1 and 2, so I'm going to pick up with example number 3 and just kind of finish it out. We have a mass of 150 milligrams that's decomposing continuously. Continuous decay, that should be e to the RT. And we see that in this equation. The weight of this 150 milligram mass as it decomposes is modeled as A of t, the weight at time t, is equal to 150, the initial mass, times e to the negative 0.042 t, where t is measured in hours. What's the half-life of this mass? Well, if you remember what a half-life is the amount of time it takes for a mass to decrease to half of its size. In this case, we want to decrease from 150 to 75. So here's our initial structure. 75 equals 150 times e to the negative 0.042 t. I've divided each side by 150, 75 over 150. Hey, there's a half-life, 0.5. 0.5 equals e to the negative 0.042 t. We want to solve for t. It's an exponent at the moment. By taking, in this case, natural logs, I can say the natural log of 0.5 is equal to the natural log of e to the negative 0.042 t. What's the goodness about this? Well, there's two great things about what's happening on the right-hand side. Number one, I can bring this power out front. ln of 0.5 equals negative 0.042 t. Times what? The ln of e. I said there were two great things. Well, the power coming out was one. The second lovely thing is that the natural log of e is nothing more than 1. And so what am I left with? I'm left with the ln of 0.5 equals negative 0.042 t. Solve for t, and I'll come back with t equals ln of 0.5 over negative 0.042. Let's roll to my calculator. ln 0.5 divided by negative 0.042. And I come up with an answer of 16.5. 16.5 is t. That's how many years it will take me to reduce my mass from 150 to 75. The half-life is 16.5 years in this case. All right, on we go. Or t measured in hours, 16.5 hours. Let me just kind of correct that last piece there. Okay, next problem, compound interest, continuous compound interest. An investment of $2,000 is going to compound continuously with an annual interest rate of 7%. How long will it take, how many years, until the investment is worth $5,000? Well, first and foremost, we should know this is our good equation. P of t, the amount of our investment's value, is 2,000, the original, times e, continuous growth, continuous compounding, e to the RT. R is 7%, 0.07. 2,000 times e to the 0.07 t. We want our investment to be worth how much? $5,000. So we want to set P of t equal to 5,000. If we do a little bit of work, what do we know? I can divide each side by 2,000. 5,000 over 2,000 gives me 2.5. So I know that 2.5 equals e to the 0.07t. This problem now has become very similar to the one that we just did. I can do what? I want to solve for t, it's an exponent. I'm going to take an ln of each side. ln of 2.5 is equal to the ln of what? E to the 0.07t. Again, those two great things happen. First and foremost, the power moves up front. Anytime you're taking a logarithm, something to a power, you can drag that logarithm out front. We're left with just the good old ln of e, which we've already said is 1. We did that before. We're good with that. And so I know that the ln of 2.5 is equal to 0.07t. And how do I solve for t? Divide left and right by 0.07. I know that the value of t is equal to the ln of 2.5. ln 2.5 divided by 0.07, 13.1, let's say if we round. 13.1 years is how long it's going to take for me to get this investment up to 5,000. One more to work with. What's that last problem that we have? Oops, excuse me. An investment of $1,000 earns earns 12% interest, compounded quarterly. How long to the investment to triple? Well, what do I know? I need to build my formula first. I'll just say P of t equals initial amount, 1,000, 1 plus r, in this case 0.12, divided by what? We are compounding quarterly, divided by 4, and to the what? nt, to the 4t. 0.12 divided by 4 is 0.3. P of t equals 1,000 times 1.03, excuse me, to the 4t power. I want my investment to be equal to what? $3,000. I want it to triple. Divide each side by 1,000. 3 equals 1.03 to the 4t. Just as before, take logarithm this time rather than e. I don't have a e in my equation here for my rate or whatever, so in this case, just going ahead and working this way. It's going to be a little bit simpler for me, so I'm going to say log of 3 equals the log of 1.03 to the power 4t. As before, log of 3 equals the log, equals, drag the power up front, sorry for the camera move there, log of 3 is equal to 4t, power comes up front, times the log of 1.03. I want to solve for what? T. Well, I can say log of 3 over log of 1.03 equals 4t. And if I want to solve straight for t, I'd have log of 3 over 4 times the log of 1.03 equals t. Calculator time again. Logarithms this time. So, log of 3. And I'm going to do what? I'll kind of do it a step at a time. I'm going to divide by 4. And I'm going to take that answer, and I'm going to divide by the log of 3. Of 1.03, excuse me. And there's my answer, 9.29. T is equal to 9.29. That's the number of years it's going to take for my investment to triple. So that's how we work through solving exponential equations. Let's look at a couple of others. Let's pretend that we have, not pretend, let's actually have one. We have a logarithmic equation that we're asked to solve. How can I handle that? Exponentiate each side. So use the other principle. One of the quick ones is to say rewrite your logarithm. That's another way in which we can express this. Take advantage of how we know that good old popcorn method to rewrite a logarithm as an exponent. So we're just going to do one example here. I'm going to write it a little bit bigger on paper here, and then I'll transfer the camera over. I have the log base 4 of 2x minus 6 equals 4. How can I solve this? Well, our popcorn method could be pretty helpful here. 4 to the 4th power equals 2x minus 6. 4 to the 4th power equals 2x minus 6. A little quick work. There we are. There's our popcorn written out. 256 equals 2x minus 6. That's what 4 to the 4th is. Add 6 to each side. 262 equals 2 to the x, equals 2x. And finally, last piece, what? Divide by 2. X equals 131. We're solved and we're good to go. So whenever you see these types of problems, just kind of take advantage of what you have. Don't be afraid. Rewrite it as a what? As an exponential. And chances are you'll be in pretty good shape to solve this. So there's one more piece that we want to do. More advanced problems. We have more consolidated logarithms. We have more detailed pieces that we need to solve. How can we handle this? Well, the box gives us a good way to work through this. Take advantage of properties wherever you can to simplify combinations, put things together into a consolidated logarithm. Do the same thing before if you need to. Exponentiate as appropriate. If you get into a situation where you have log of x, I'm just going to use 2 letters at the moment, equals the log of q, 2 arbitrary letters, what do you know? You know that x equals q. Use that equivalency process to help you out. So let's work through some of these problems and see what we can get. There's one other caveat that we'll talk about after we work through each of these problems as well. So our first one we're asked to solve is ln of x minus 1 plus the ln of 6 equals the ln of 3x. Well, it'd be nice to have one consolidated logarithm on each side, or a consolidated ln in this case. And we can do that because we can use what? The product property. ln of x minus 1 plus the ln of 6 is the same as the ln of, here we go, 6 times x minus 1. And that's the same as, what's 6 times x minus 1? To distribute that 6 to x minus 1, I gotta have the ln of 6x minus 6. And that needs to be equal to the ln of 3x. Do I have an ln of something equal to the ln of something else? Sure thing. And what do I know about these two things? They better be equal to each other. 6x minus 6 equals 3x. Take the 6 over to the right. Bring the 3x to the left, and I have nothing more than 3x equals 6. X equals 2. Now, whenever you solve a logarithmic problem, one of the things you want to make sure is that the values, the solutions that you come up with, work in the original equation. You have to make sure. It's not just to solve algebraically. We need to be able to solve in the context of the original logarithm. And remember, you cannot take the log of a negative number. You can't take the log of 0. In your original equation, you must ensure that you are always taking the logarithm of a positive number. If x equals 2 is a solution, am I good? Yeah, I'd be taking the log of 1 here. The ln of 6 obviously is okay. And the ln of 3 times 2, I'd be taking the log of 6 again. I am fine. X equals 2 is a good, acceptable solution. Next problem, L of x plus 14 minus log of x equals the log of x plus 6. Again, it'd be nice to consolidate the left-hand side into a single log, which we can do using the good old quotient property. I'm going to have the log of, sorry for the camera move there, log of x plus 14 over x equals the log of x plus 6. Good with that, hopefully. What can I do? Again, log of something else. They got to be equal to each other because there's those lovely equal sign right there. I know that x plus 14 over x equals x plus 6. I'm going to go ahead and distribute the x in the numerator over on this side as I cross multiply. And I'm going to say x plus 14 equals x squared plus 6x. I'm going to bring everything over to the right side. I'd have x squared plus 6x minus x minus 14, and that would be equal to, on the left-hand side, 0. So take a look. I went from here over to this step by moving everything to the right side, setting the left equal to 0. I have 0 equals x squared plus 5x minus 14. Can I solve this? Yeah, I can factor that. x plus 7, x minus 2 equals 0. Solutions, x equal negative 7, x equal positive 2. So that's my structure. Now what do I need to do? I need to see if the algebraic values, x equal negative 7, x equal 2, can they work? Well, let's look. Original equation. Let's do the x equal 2 first. Well, 2 plus 14, that's good. Log of 2, no sweat. Log of 2 plus 6, 8, absolutely. It's all clean. X equal 2 is a good solution. X equal negative 7, well, log of negative 7 plus 14, I'd be taking a log of positive 7. That's all right. But look what here, minus the log of what? Negative 7. I can't take the log of negative 7. What's that tell me? As soon as whenever you're checking, any of your logs require you to do something that you're not allowed to do with logs, you can invalidate that potential solution. I reject this solution. My final answer is nothing more than x equals 2. So even though algebraically there's a couple pieces that fit, you have to work in the context of the original equation to see whether a solution algebraically can actually be accepted logarithmically. Okay, a couple more to go. Log base 2 of x minus the log base 2 of x minus 2 equals 3. Note, not seeing logarithms this time on both sides, but let's talk our way through this very quickly. Let's consolidate and see what I can say. I can say that the log base 2 of x over x minus 2 equals 3. I can say that, no problem, using my properties, my quotient properties. And I could also take advantage of what we did in our top example on this page. I got a logarithm equal to a constant. I could do a very quick popcorn and say 2 to the third equals x over x minus 2. 2 cubed is 8. I could say 8 equals x over x minus 2. Cross multiply, 8x minus 16, distributing x minus 2 against the 8, is equal to x. 16 goes to the right, x goes to the left, 7x equal 16, x equals 16 over 7. Original equation, 16 over 7, fine here. 16 over 7 minus 2, well, that works. 16 over 7 minus 2. Well, that's 14 over 7. 16 over 7 minus 14 over 7. I still would have a positive number. I am good with the x equals 16 over 7. Now, let's look at this problem one more time, just in a slightly different context. I'm going to rewrite log base 2 of x over x minus 2 equals 3. And what I'm going to ask is, could I rewrite 3 as a logarithm with a base of 2? So look at this real quick. See what I put over here. Log base 2 of 8 equals 3. Check and see if you agree with that. I hope you do, because it's accurate. But this would allow me to do what? I could say that the log base 2 of x over x minus 2 is equal to the log base 2 of 8. I've just rewritten what? 3 as log base 2 of 8. Can I now walk into x over x minus 2 equals 8? I sure can. Does that look relatively familiar to what we saw over here when we kind of did a popcorn method? Absolutely. So what you kind of find is there might be a couple ways in which you can solve these problems. My general thought is using the popcorn method and just kind of rewriting is the simplest way, but you're welcome to try either method. Whatever gets you there is more or less fine. One more to go. Log of x minus 2 plus the log of 3 equals the log of 5x minus 7. Got logarithms on each side. Let's go ahead and try to consolidate. Here's the equation one more time. What can I do? Product property. This becomes distribute to 3 log of 3x minus 6 equals log of 5x minus 7. There's the writing, and we'll continue from here. I know that 3x minus 6 equals 5x minus 7. Again, let me move the camera. What can I do? Well, I can roll the 7 over here. I'll roll the 3x to the right, and I would come back with 1 equals 2x. In turn, that tells me that x equals 1/2. All right, fine. Only have one potential solution to check. X equals 1/2. Well, log of 1/2 minus 2, I'd be taking what? The log of a negative number. Can I rule this solution out? My x equal 1/2? Absolutely. Does this have any solution, this problem number 4? The answer is it sure doesn't. The only algebraic number that made some sense with a candidate was x equal 1/2. I had to reject that. There is no solution. So this is the process of solving exponential and logarithmic equations. Be comfortable. Don't be afraid to use the power property. Know how to use your logarithm property so you can create consolidated logs. As you see in these problems, that was an essential way of solving them. This covers the rest of section 4.5. You can work your way through the homework, check out these notes one more time, and I think you'll be in good position for this particular section.